For section 5.4, we'll be looking at the remaining trigonometric graphs, with most of our time spent focusing on the tangent graph and transformations of the basic tangent graph. So for the function y equals tangent of x, a note here, we're going to determine that the period of the tangent function is pi. The amplitude is not defined. That's because amplitude, when it is defined, is calculated as the difference between the maximum and the minimum of a function. And the tangent has no maximum and it has no minimum, as we'll see, that the tangent approaches vertical asymptotes, in fact. Okay, so this changes a couple of things from our study of the sine and the cosine waves. First off, the amplitude is not defined simply for the tangent graph, and this will also be true for the other three trigonometric functions, the cotangent, the cosecant, and the secant. They all have vertical asymptotes, and so none of them would have a defined amplitude. But also it changes the quarter point structure, because now 2 of the 5 locations of the quarter periods, the beginnings and the endings of quarter periods, 2 of those 5 would be vertical asymptotes. And in fact, we're going to have vertical asymptotes for the tangent between negative pi over 2 and pi over 2. We'll have a vertical asymptote at negative pi over 2 and another one at pi over 2. We'll see why that has to be the case as we construct the graph, the basic graph of the tangent function, by using our already determined geometric definition of the tangent. And finally, another attribute of the tangent function is that it is odd, and an odd function satisfies this symbolic relationship, f of negative x equals negative f of x, which is represented also on the graph as a type of symmetry, a symmetry about the origin, which can be seen as either a double reflection or a rotation through 180 degrees. So for example, if we have a point up here in quadrant 1 with coordinates x, y, if we reflect it over the y-axis and then over the x-axis, we would find another point that is also on the function, if it is odd, another point with coordinates negative x, negative y. Right, so you change the sign of the input and you change the sign of the output when you have a function that is odd. The same would also be true if we had a point that were in quadrant 2. By a double reflection, it would have a reflection of itself in quadrant 4, and we call that symmetry about the origin. So this is characteristic of an odd function. Okay. So, and I'll note here, no defined amplitude, okay, because the tangent has no max and no min. Okay, no max and no min. All right. Okay, so after we create the basic tangent graph, we'll do some transformations. We'll focus mostly on A, B, and C, but we can also consider the vertical shift, certainly. So A, we're not going to refer to that as having anything to do with amplitude for tangent graphs, but it will still have an effect on stretching the graph vertically, right? And also reflecting, right? Okay, so let's see. So K is still going to be a vertical shift, okay, of the basic graph, either up or down, depending on whether K is positive or negative. If A is less than 0, then we're going to end up seeing a vertical reflection. Okay. If A is greater than 0, then there's no vertical reflection. And the magnitude of A, can indicate whether there is going to be a stretch, okay, or a compression vertically, okay, a vertical stretch or compression, that is. Okay. B can still be thought of as the frequency. We can use, if B is negative, we can use the odd nature of the function in order to factor out the negative. All right, so B less than 0. Okay, use the fact that the function is odd, as we did with the sine function previously. Okay, remember the cosine function was even, so we did something similar with the cosine function when B was negative, but that dealt with it being even. So if B is negative, if there's a negative coefficient to x, we can factor the negative out of the argument, and then we can move the negative to the front, okay, to cause a vertical reflection then. The magnitude of B can then be used in order to determine the period. Okay, so the period for the tangent that has been modulated is found by taking pi and dividing that by the magnitude of b. So I'd like to draw special attention to that. Okay, that is slightly different for the tangent than it was for the sine and the cosine, because for the sine and the cosine it would be 2 pi divided by the magnitude of b. Okay. For the tangent it is pi divided by the magnitude of b. Okay. That's what gives us the period of the modulated tangent wave. And finally, c is the phase. Okay, so we're going to have a horizontal shift. The horizontal shift can again be found by setting bx plus c equal to 0. If you set bx plus c equal to 0, then you solve for x. All right, then you're going to get x is equal to negative c over b. Okay, that's going to be the horizontal shift. Okay, so quite similar to what we've already done before. Just draw attention to how we find the period of a modulated tangent function. We're dividing pi by the magnitude of b instead of 2 pi. And we, in general, refer to the magnitude of a as a vertical stretch or a vertical compression of the graph, but we no longer refer to it as an amplitude because the tangent does not have a defined amplitude. Okay, the other basic trig graphs, we'll take a look at each of those as they are reciprocals then of the 3 trigonometric functions we already have graphs for, right? Cotangent would be the reciprocal of the tangent. The cosecant is the reciprocal of the sine, and secant is the reciprocal of the cosine. And so I'll show you how you can use the fact that they are reciprocals in order to construct the graphs of these 3 reciprocal functions. Okay, so let's examine the tangent function geometrically here. How do we get the basic tangent graph? So I'm going to graph y equals the tangent of t. So we can use the input t to refer back to our geometric interpretation of the tangent function, where t is the arc length within the unit circle. All right, this is our unit circle, of course. We can see that the radius is equal to 1, and it's centered at 0, 0 by looking at the coordinates of these 4 points. So recall that if we travel a distance t in standard position on the unit circle, the terminal point that we end up at will have coordinates x, y, where we have defined that y is equal to the sine of t, x is equal to the cosine of t, and we have defined that the tangent of t would be the ratio y over x. Now recall that this also means, geometrically, we could interpret the tangent, this is not tangent of x, right? Tangent of t, there you go. Right? Recall that we can interpret this as well as the slope of the line that connects the center of the circle to the point with coordinates x, y. Okay, so we draw a line out like that. Okay. Then the slope of that line, the slope of this red line right here, would be found by y2 minus y1 over x2 minus x1, where y1 and x1 they both equal 0. So we have y minus 0 over x minus 0. All right, so y over x. All right, so we can visually, geometrically represent the tangent as being the slope of this line as t changes. So for whatever t is equal to, we have a terminal point. We can draw the line back to the center. The slope of that line is our interpretation for the tangent. So let's take a look at some different values, therefore, of the tangent by that interpretation. Okay, maybe a table of values would help here. So some values of t and the associated tangent of t by considering the slope of the associated line. If t is equal to 0, all right, I'll even write here that I'm considering the slope. If t is equal to 0, then we're at this initial point 1, 0. Then the line that we're talking about would be this line right here. And clearly that line has a slope equal to 0. So the tangent of 0, okay, the tangent of 0 is equal to 0. Now, as t increases to, let's say t increases to pi over 4. So we'll recall that t is equal to pi over 2 by the time we hit the positive y-axis. While t is equal to pi when we get to the negative x-axis the first time. T is equal to 3 pi over 2 if we are rotating counterclockwise in standard position. T equals 3 pi over 2 corresponds to being on the negative y-axis, and then t is equal to 2 pi if we go through a full rotation and come back again to the starting initial point at 1, 0. Okay, so if t is equal to pi over 4, we are halfway through quadrant 1. And if we're halfway through quadrant 1, we recall that the x-coordinate and y-coordinate would be the same as each other. Right? In other words, we know that the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is also root 2 over 2, and the tangent can be defined as the sine divided by the cosine as well. Alright, tangent is also defined as the sine of t over the cosine of t by identity. So, the tangent of pi over 4 is equal to 1. Because the x-coordinate and y-coordinate are equal to each other. Okay, continuing on. What happens as we approach pi over 2? If we were to choose the point on the unit circle whereby t would equal pi over 2, so that's right here, so we have traveled up to this point right here, the associated line that we would draw, notice, is a vertical line. And of course the slope of a vertical line is undefined. So, the tangent of pi over 2 is therefore undefined. Okay? So we went from the tangent of 0 was equal to 0, the tangent of pi over 4 was 1, and then ultimately to tangent of pi over 2 is undefined. Now what happens if we were to choose values that are just a little bit less than pi over 2? That is, what happens as t approaches pi over 2 from below? So if we choose values that are getting closer to pi over 2 but remain less than pi over 2, and what does the geometry tell us then? Well, so for example then, let's say that we choose a point on the unit circle that's getting close to pi over 2 but hasn't quite hit pi over 2 yet. All right, notice the slope of this line right here is going to be very, very positive. All right, so we're going to have a very positive slope here. That's the closer that this point gets to the y-axis, the more positive that slope is going to be. Right? Steeper and steeper the closer we get. And ultimately, we're getting to an undefined slope there. So, we can see that then, as t approaches pi over 2 from the left, okay, the tangent of t is approaching an uncountably large slope, a positive slope that is approaching an undefined value. It's approaching positive infinity. And what happens then if as we just pass pi over 2? What if we go just to the left of there into quadrant 2? So now I'm thinking about t is a little bit more than pi over 2 because we traveled a little bit more than a quarter of the circle at this point. Notice now that the slope of this line, okay, is in fact negative. And the closer it is to pi over 2, the closer this point is to the y-axis, the steeper this line is going to be. The more extreme that slope is going to be, but it's going to remain a negative slope. Okay. So we can say as t approaches pi over 2 but remains a little bit more than pi over 2, the associated tangent of t, interpreted as the slope of that line, is very, very steep but negative. So the tangent of t would be approaching negative infinity then, on the other side of pi over 2. Alright, so let's plot some of these features so far here, through quadrant 1 and a little bit into quadrant 2. Let's plot those on our graph. So we have, when t is equal to 0, the tangent of t, which is the y-coordinate, is also equal to 0. Alright, so we have a point right here. at 0, 0. And then if t is equal to pi over 4, okay, I'll move that up a little more than that, okay? There we go. So if t is equal to pi over 4, and the tangent of t is going to equal 1. So let's put 1 on the y-axis here. Okay, so we have a point like right there. And then as we move out to pi over 2, what is happening? It's undefined at pi over 2, but we see that as we approach pi over 2 from the left, the tangent function is going towards positive infinity. That's asymptotic behavior, okay? As is in the other direction, that's asymptotic behavior. Okay? If t is just a little bit more than pi over 2, the tangent of t would be approaching negative infinity then, right? So we have a vertical asymptote, therefore, at t equals pi over 2. From the left, this is approaching in this direction, so we have a curve that is moving outward like this, okay, and asymptotically approaching that line at pi over 2. And then on the other side of pi over 2, we have the function looks like this, right? It's approaching the asymptote as it goes towards negative infinity instead. Now let's continue then into quadrant 2. Let's see what happens now. What if we move to where, let's go to 3 pi over 4. Right? Once t is equal to 3 pi over 4, puts us squarely in quadrant 2, halfway through quadrant 2. The associated slope of this line, okay, we know that the x-coordinate is going to be negative, the y-coordinate is going to be positive, but their magnitudes would be the same as each other, by symmetry the same as we had in quadrant 1 at pi over 4, because the reference was pi over 4. Okay, but now the ratio of y over x is going to give us a negative quantity. Okay, so the tangent of 3 pi over 4, which is the same as the sine of 3 pi over 4 over the cosine of 3 pi over 4, is going to be negative 1. Right? Again, we can just use reference. We have that the reference was pi over 4, and the tangent of pi over 4 was already 1. That gives us the magnitude. Now, because 3 pi over 4 is in quadrant 2, where the tangent is negative, therefore we make our output negative. So negative 1. Okay, so let's include that on the graph. So we go out to 3 pi over 4, and the output is negative 1. Okay, so I should have a point right around here. So this graph should smoothly and continuously approach that point. Okay. All right, let's continue now to where t is equal to pi. When t is equal to pi, the line we're talking about is this line right here, right along the x-axis. And that line, again, has a slope equal to 0, just like this line did over here. So when t is equal to pi, the tangent of t is equal to 0. So the tangent of pi is equal to 0. So our graph should include a point, okay, where right, t is equal to pi. Okay, the y-coordinate then should be 0. And so we've returned back to the t-axis in this case. All right, now what's going to happen then as we transition into quadrant 3? Let's continue our table of values. T versus the tangent of t, interpreted as the slope of that line. Or as the sine of t divided by the cosine of t would be fine as well. All right, let's move to 5 pi over 4. That puts us halfway through quadrant 3. Okay. The coordinates of the terminal point would both be negative, so the ratio of them is going to be positive. We can see that. The slope of this line is, in fact, exactly the same as the slope of that line right there. The same slope, right? As long as they have the same reference number, that is. And they do. This has a reference number of pi over 4. And this one had a reference number of pi over 4. Okay, so tangent of 5 pi over 4, that is, okay, is equal to positive 1. All right, so we've returned back to positive 1 again. And the behavior of this graph is then going to continue the way that it did previously. It's going to continue upward like that. We have repeating behavior now. Okay, we're going to approach another asymptote. And where's this next asymptote going to be located at? All right, we had an asymptote at pi over 2. This next asymptote would be located the next time we have an undefined slope. That's when if we were to choose t to equal 3 pi over 2. Because by the time we get to 3 pi over 2, then we're talking about the slope of this line right here, and the slope of that line is again undefined. And notice the asymptotic behavior around 3 pi over 2, tangent of 3 pi over 2 is undefined. Okay. As t approaches 3 pi over 2 from below, so from less than 3 pi over 2, right, so if we choose t to be a little less than 3 pi over 2, then we're talking about geometrically the slope of this line right here. Notice the slope of that line is going to be positive. Throughout quadrant 3, the slope is going to be positive. And it's going to get more and more positive. It's going to be steeper and steeper the closer we get to where t is 3 pi over 2. So as t approaches 3 pi over 2, okay, the tangent of t would be approaching positive infinity, okay, as we see here in this graph. Now what happens after we pass by 3 pi over 2? What if we choose a value of t that's a little bit more than 3 pi over 2? Then we're talking about the slope of a line that is very, very steep but negative. So here the slope is going to be negative. So as t approaches 3 pi over 2 from above, then the tangent of t is approaching negative infinity. And again, we have asymptotic behavior. So on the other side of the 3 pi over 2, we would expect then the graph is going to, again, approach this asymptote in this direction like it did here. So this wave is going to repeat. Would it have repeated if we went back in this direction? We should expect that it certainly would. Now we can examine that by choosing negative values of t. For example, okay, like if I choose t to equal negative pi over 4, that would put us on the unit circle right here in quadrant 4. Okay. And in quadrant 4, we have the coordinates are, let's see, the x-coordinate is positive, the y-coordinate is negative. Of course, the slope is less than 0. Okay, so if we choose t is equal to negative pi over 4, it puts us halfway through quadrant 4. The reference is pi over 4, so the magnitude of sine and cosine are the same. That's the magnitude of the y and x coordinates are the same, but they're opposite in sign. So the tangent, being the ratio of those two, would then be negative. Okay, -1, in fact, right? If t is equal to negative pi over 4, then the tangent of that, that's the tangent of negative pi over 4, is equal to -1. So at negative pi over 4, we have a point at -1. This is smoothly and continuously going to reach that point, and then we're going to continue downward in this fashion. All right, we should expect to approach another vertical asymptote here. That vertical asymptote would be found where t is equal to negative pi over 2. Negative pi over 2 would put us right here on the negative y-axis. Again, the slope of the line is undefined, so the tangent would be undefined. And then the pattern is going to continue to repeat after that as well. Okay, the next point over here where it's going to intersect the axis, what would be the coordinate there? Okay, so there's our graph, our basic graph of the tangent function, and we're going to focus on the principal branch of this function being between negative pi over 2 and pi over 2. Okay, so this piece right here is our principal branch. Now the principal branch, okay, or any of these branches, why do we choose this? We choose this because it's a nice smooth and continuous wave. We could choose to go from 0 to pi, and then we'll be broken. It'll be broken into two pieces over this vertical asymptote. And sometimes, to be honest, we do choose to go from 0 to pi when examining the tangent. Okay, you can see that in Calculus 2 course, for example, or in applications, as you might see in some natural sciences, engineering, physics, for example. This could be when we're trying to relate the tangent to the secant function. So in some applications, we may choose to investigate the tangent from 0 to pi, okay, as one complete cycle. And that skips over the vertical asymptote at pi over 2. However, it's very common to consider this continuous wave of the tangent to be the principal branch. Okay? And that principal branch is bounded between negative pi over 2 and pi over 2, where we see we have vertical asymptotes at each of those input values. Okay? It includes specific points at negative pi over 4 and pi over 4, and the origin 0, 0. And there's the shape of the curve right there. Okay, so we have the principal branch, okay, of the function y equals the tangent of x, okay, is on the interval from negative pi over 2 to pi over 2. And that is an open interval because at negative pi over 2 and pi over 2, the tangent would in fact be undefined. We have vertical asymptotes there. All right, so you can graph your asymptotes. Tangent graph goes through 0, 0. It approaches the asymptote on the right, it approaches towards infinity, and the asymptote on the left, it approaches towards negative infinity. Okay? And we have points at negative pi over 4 and positive pi over 4, okay, with output equal to 1 and negative 1. Okay, so consider then for the quarter points and the vertical asymptotes, okay, we have from the left to the right, we have first a vertical asymptote at x is equal to negative pi over 2, okay, and then we have a point at negative pi over 4, negative 1. We have a quarter point at 0, 0. We have a quarter point at pi over 4, 1. And then we have another vertical asymptote at x is equal to pi over 2. Okay, so the important x values to keep in mind if you wanted to plot all the important points and asymptotes on one complete cycle of the tangent. Okay, keep in mind the values of x at negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. All right, let's take a look at a modulated tangent function. Try to graph it. Let's see. Graph y equals negative 3 tangent x. So we already know what the basic tangent function looks like. And we can say we already know also how to do basic transformations to graphs where we know the basic function, right? We know that this is going to be a vertical reflection and a vertical stretch, for example, of the tangent function, right? So we have the value of a, in this case, if we would say this is, all right, y equals k plus a times the tangent of bx plus c, right? We have a is equal to negative 3. Okay, if a is negative, then we get a vertical reflection, and the magnitude of a is equal to 3, so we're going to get a vertical stretch. All right, and that's it. So I'm going to take the basic tangent graph. All right, y equals the tangent of x. Okay. Examine its sketch between negative pi over 2 and pi over 2. We'll start with that principal branch, and then we can repeat it. Okay. Starting in that principal branch, though, you can imagine what it looks like if we were to reflect it vertically and then stretch it. So set up our axes here, x versus y. Graphing y equals negative 3 times the tangent of x. So the shape is going to be a vertical reflection of this. Okay. So something like that. Good enough. Okay. There's our basic shape. Now let's find specific points. Okay. Let's find the quarter points and the vertical asymptotes. And in general, what we can do, so this is going to work for any combination of bx plus c. Set bx plus c equal to the set of values from negative pi over 2 to negative pi over 4, 0, pi over 4, and pi over 2, and that's going to find the 5x values that we need. The vertical asymptotes will be whatever value of x we get when we set this equal to negative pi over 2, and whatever value of x we get when we set it equal to pi over 2. Okay? Now in this case, our bx plus c is just x. All right, we have b is equal to 1 and c is equal to 0 because it's just tangent of x. Okay? So, x equals the set as defined here, negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Okay? Well, then we can simply plug in to the function to find the associated y values at the quarter points. Okay? Now, we don't plug in the values that would associate with vertical asymptotes because we expect, well, if we did, we would expect to get a domain error because it is undefined. Right? So if you plugged in negative pi over 2 or pi over 2, you're just going to get undefined or error or domain error. Okay? All right, so we already know that there's a vertical asymptote then at x equals negative pi over 2 and another one at x equals pi over 2. Okay? By symmetry, we can also plot that there is halfway between here and this vertical asymptote, there is the value x equals pi over 4. Okay, that's an important point for us to plot. Okay, what would be the y value there? And halfway between the vertical asymptote on the left and where it right now crosses the x-axis, in this case, negative pi over 4. Okay, the y coordinate here, what would that be? We could find by simply plugging into the function. Right, so if we say, what is negative 3 times the tangent of, let's say, pi over 4? Right, y equals negative 3 times the tangent of negative pi over 4. Let's do that one, negative pi over 4. Because tangent is an odd function, we can take the negative and we can move it to the front. All right, because tangent of negative x is the same as negative tangent of x. So we can move this negative to the front because tangent is odd. And then we can evaluate this. The tangent of pi over 4 is 1, so we have 3 times 1, which is equal to 3. So at negative pi over 4 for the input, the output is going to be 3. So the y value right here is 3. Okay? And if we plug in pi over 4, we'll get negative 3 times the tangent of pi over 4, which is negative 3 times 1. That'll output negative 3. Okay? So that's it. And this point right here is at the origin, so this is the point with coordinates 0, 0. Okay? So we have 2 vertical asymptotes, and we have 3 quarter points. Okay? Vertical asymptote here, right? We have this quarter point, okay? This quarter point right here, this quarter point right here. We can read the coordinates off of the axes, or we can state it off to the side. All right, either case, whatever. Okay, now we can extend this graph by periodicity. That is, we can copy this image and then we can paste it out towards the right and also out towards the left. Okay. So we have one complete cycle already graphed here. Okay, then I want to just repeat the image. Okay, eventually we'll approach another vertical asymptote. Okay, and on the other side as well. Okay, so we have a wave out here, something like that. Okay, and it approaches a vertical asymptote out in this direction. Okay, all right, so where would this vertical asymptote be positioned? Where would that vertical asymptote be positioned, for example? Well, you can see that the period, let's see, the period for this wave is the length of this complete cycle. That's the distance between consecutive asymptotes, for example. Okay. The standard period of a tangent function is equal to pi. Okay. The period of our modulated tangent function is found by taking pi divided by the magnitude of b. And the magnitude of b here is equal to 1, so we just have pi over 1, so the period is equal to pi. Okay. All right, so if we were to add pi to, let's say, pi over 2, we would find the next vertical asymptote. Okay, so that would be at x is equal to 3 pi over 2. All right, because that is what, pi over 2 plus pi, so we've added the period. And if we were to subtract pi from negative pi over 2, that would put us at x is equal to negative 3 pi over 2. Okay, from subtracting pi, a full period, from negative pi over 2. Fix this graph a little bit here. Do a little better here with the symmetry. So about halfway between these two asymptotes, there's a point. Okay. I think that's a little bit better. So if we wanted to find the coordinates for this point right here on the x-axis, that would be found a full period away from the origin. Okay, and a period is pi, so this is pi less than 0. Okay, so this has to be a point at negative pi. We can check in the function that if we plug negative pi in, we should get 0 as the output. That is, negative 3 times the tangent of negative pi should output 0. And it does. Negative 3 times the tangent of negative pi. Again, using the fact that tangent is odd, we can pull this negative to the front. So we get 3 times the tangent of pi, which is 3 times 0, which is just equal to 0, for example. Okay. All right, so we can always go back to the function and we can plug in an x value to see what the associated y value is to make sure that the equation is agreeing with the graph and vice versa. Okay. All right, so that's at negative pi. Okay, what about this point if we want to know where that is, or this point as well? Right? What is this x-coordinate? What is this x-coordinate right here? Right? Well, this point right here, let's say, that would have to be a full period to the left of this point right here. So that's pi less than negative pi over 4. So that would put this point at negative 5 pi over 4 for the x value. The y coordinate is 3. Okay, right here, this is this point right here, right, is pi to the left of this point. This point was at pi over 4. Pi over 4 minus pi is negative 3 pi over 4 then, for example. All right, so we can continue this in both directions if we wish. All right, on each complete cycle, we can plot 3 quarter points and 2 vertical asymptotes as well. Okay. All right, so this would be, let's see, so this point right here is going to have to be at pi. Okay. This point right here is pi more than negative pi over 4, so that puts this at 3 pi over 4. And this x-coordinate right here, this has to be a distance of pi from pi over 4, so this has to be at 5 pi over 4. Okay, we can continue this indefinitely if we wish. Okay, let's try another example now. Let's do this. Graph one complete cycle and label the quarter points and vertical asymptotes. Y equals, let's see, the tangent of 2x minus pi over 2. So if we consider in general, y equals k plus a tangent the quantity bx plus c. Here we have, well, first we have k is equal to 0. We have a is equal to 1. Right? We have b is equal to 2, which is already greater than 0, so we don't have to deal with the odd property of the tangent function in this case. Okay. We have c is equal to negative pi over 2. Okay. All right, we have a tangent where a is greater than 0. Okay, so we can think of the basic shape of the tangent curve, which is this kind of a wave right here. Okay, so it is increasing, okay, between its vertical asymptotes for any typical period that we might decide to investigate. Okay, now I'm going to find the specific locations of the quarter points and the vertical asymptotes by setting bx plus c equal to the set of values negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2, and solving for x in each case. All right, so we have 2x minus pi over 2, 2x minus pi over 2, so I'm going to set that equal to negative pi over 2. And then 2x minus pi over 2, set that equal to negative pi over 4. And then 2x minus pi over 2, we'll set that equal to 0. And then 2x minus pi over 2, we'll set that equal to pi over 4. And then 2x minus pi over 2, we'll set that equal to pi over 2. Okay. Now some notes to make on this set of 5 linear equations. All right, they're all linear equations for us to solve for x. Okay. First, when we solve this equation here, okay, we're going to get the vertical asymptote. It's going to be the left vertical asymptote, in fact. Okay, this is going to be the left vertical asymptote for our complete cycle. Okay. And when we solve this one down here, because it's associated with pi over 2, where that would have been a vertical asymptote, when we solve this for x, we're going to end up getting our right vertical asymptote for the wave. Okay? And also, when we solve this one right here, the one where we set it equal to 0, this will tell us the location, it'll tell us what the horizontal shift is, which tells us how far from the y-axis this graph has shifted, and in what direction as well. Okay. All right, so in order to solve these equations, the algorithm is the same throughout for all 5. There's 2 steps. First step is add pi over 2 to the other side, right? Add pi over 2, and then divide by 2. It's the same process for all 5 of these. So we just apply that algorithm. So I'm going to add pi over 2. Okay, add pi over 2. To get this first one is going to be 2x is equal to 0 when we do that, right? The second one, when we add pi over 2 minus pi over 4 is equal to pi over 4, right? Add pi over 2 in the third equation, we get 2x is equal to pi over 2. In the fourth equation, we're going to get 2x is equal to 3 pi over 4. And in the fifth equation, we're going to get, 2x is equal to pi, right? Just showing that the algorithm is the same no matter which one of these equations we're looking at. Then we divide by 2, or multiply by 1/2. Okay, so in the first one we get x is equal to 0. Therefore, there is a vertical asymptote at x equals 0. The next one, we're going to get x is equal to pi over 8. Okay, the third equation, we're going to get x is equal to pi over 4. That would be the amount of the horizontal shift. This tells us that the wave has been shifted to the right by pi over 4, okay, when compared to the standard tangent wave. Let's see, multiply by 1/2. In the fourth equation, x is equal to 3 pi over 8. And in the fifth equation, we will have a vertical asymptote at x is equal to pi over 2. We have a vertical asymptote here. We have a vertical asymptote here. Okay. And this is the amount of the horizontal shift. And we can go ahead and start creating our graph now. All right, we have no vertical shift happening. Notice the vertical stretch is just equal to 1. Okay, and the vertical shift is equal to 0. Okay. All right, so we have a tangent wave bounded between vertical asymptotes. All right. The vertical asymptote on the left, we said, would have equation x equals 0. That would be the y-axis then. And on the right, vertical asymptote is at x equals pi over 2. Okay? We have a point in the center, okay, where x is equal to pi over 4, okay, by plugging into the function itself, right? Okay, plugging in pi over 4, right, we get y equals the tangent of 2 times pi over 4 minus pi over 2. Well, that's exactly equal to the tangent of 0, which is equal to 0. So this point right here, okay, has coordinates pi over 4, 0. In other words, it is right along the x-axis. Okay? And of course, again, this is the y-axis right here. It is our vertical asymptote. Okay, I can put the vertical asymptote in red so it'll stand out a little bit better maybe. Okay, so this is 3 of our 5 important locations. 2 vertical asymptotes and 1 of the quarter points. Okay, so halfway between the left asymptote and this central point, we find the x-coordinate pi over 8, and the associated y-coordinate for this function, you can find it by plugging it into the function itself, certainly, if you didn't know what it was. Y equals the tangent of 2 times pi over 8 minus pi over 2 is the tangent of, what is this, pi over 4 minus pi over 2. That is negative pi over 4. By using the fact that tangent is odd, this again is negative the tangent of pi over 4, which is equal to negative 1. Okay, so the y-coordinate is certainly negative 1. Just verifying the equation is agreeing with what we're saying is happening on the graph here. Okay, and then we have one more point. Okay, the vertical stretch was 1, so the y-coordinate here is also going to be 1, and the x-coordinate was 3 pi over 8. Okay, so that completes our graph. Of one complete cycle, that is. This completes our graph of one complete cycle. Okay, and we've labeled the quarter points and the vertical asymptotes. Now, if we wanted to continue this, we certainly could. We could repeat this. Okay, the same pattern would repeat again and again in both directions. Okay, and we could label more points if we wish. All right, okay, so this repeats indefinitely. Okay. What is the period for this function? Something we could have found. All right, the period is found by taking pi divided by the magnitude of b. In this case, that would be pi divided by 2. So the period is pi over 2. Can we verify that from the graph? All right. So the distance between the consecutive vertical asymptotes, that would be the period, and that difference right here we can see is clearly pi over 2, as would also be the distance between, let's say, you know, this central point here and the next central point. That distance would also be equal to 1 period, which is also pi over 2. Okay, the horizontal shift, all right, we could have calculated that by setting bx plus c is equal to 0. In other words, by solving x equals negative c over b. And in this case, then, that would be, let's see, negative c would be pi over 2, and b is equal to 2. Pi over 2 divided by 2 is pi over 4. So the horizontal shift is pi over 4, and it's exactly what we found here. Okay, so the central point that on a basic tangent graph went through 0, 0, that central point now goes through pi over 4 on our complete cycle that we graphed here. Okay, and again, no defined amplitude, because there is no maximum, there is no minimum. All right, so I'll make a note here again about that. There is no defined amplitude, since the graph has no max and no min. Okay, by virtue of the asymptotic behavior here. Okay, let's take a look at the reciprocal functions now. Let's start with the cosecant graph. Okay. Graph y equals the cosecant of x. Okay. So cosecant of x, cosecant of x is equal to 1 over the sine of x. Okay, that is, if we can consider the y values for the sine function, the reciprocals of those y values would tell us the y values of the cosecant function. Let's take a look at the sine curve. Okay, call a basic sine wave. All right, so here in black I have graphed y equals the sine of x. Okay, some of the important points here. Let's see. This would be pi over 2 right here, and the output was 1. This is pi, where the output was 0. We have at 3 pi over 2, and the output was negative 1. Okay. We also had over here negative pi over 2, or the output was negative 1. This is negative pi, right? We have negative 3 pi over 2. The output was 1 right there. Okay, this is negative 2 pi. This would be 2 pi, right? This is 3 pi. For good measure, I guess one more. How about 5 pi over 2, 1. Okay, that's enough right there. So y equals the sine of x. So if we think of the y coordinate of the sine function for a given x value, the cosecant of x is the reciprocal of that. Okay, so this is equal to 1 over y, okay, if y equals the sine of x. Okay, so let's take a look at a table here, for example. So we have x versus sine of x versus cosecant of x, for example. Let's say I take x is equal to pi over 2. If x is equal to pi over 2, the sine of x would equal 1. And the cosecant of x, which is 1 over the sine of x, would be 1 over 1, which is equal to 1. Right? Okay, not too different at like 3 pi over 2. At 3 pi over 2, the sine of x is equal to negative 1. And the cosecant would be 1 over negative 1, which is also negative 1. Okay, so we already have a couple of points we can graph. Right, in red now for the cosecant function. Okay. So this point right here, pi over 2, 1, is on both the sine curve and the cosecant curve. 3 pi over 2, negative 1 is on both the sine curve and the cosecant curve. And then by symmetry, periodic symmetry, that would have to be true at all of these points as well. All right, those are on both of the curves. Now, what happens at a place like 0? Okay, when x is equal to 0, the sine of x is equal to 0, well then the cosecant would be 1 over 0, but that is undefined. Well, what does that mean? Okay, it means we expect some sort of a discontinuity there, right? Probably an asymptote. Well, what happens as x approaches 0, let's say from the left? As x approaches 0 from the left, well, the sine function, okay, the sine of x, so we're saying if we're along this curve just a little bit to the left of the origin, then the sine function is going to output a small negative number. So the sine of x is going to be is going to be a little bit less than 0. It's going to be a negative quantity, right? And what happens to the cosecant then? If you take 1 divided by a really small negative number, okay, you're going to get a really, really large, okay, you're going to get a really, really large negative number, right? So this is approaching negative infinity. Okay, so I'm not dividing by 0, but I'm dividing by a really, really small negative number, because that's what the output of the sine function was there. What happens as x approaches 0 from above? That is, what happens if we choose a value of x that's just a little bit more than 0? Well, the associated y value of the sine function is going to be a little positive number, right? A small positive number. And what happens when we take the reciprocal of a very small positive number? Okay, the reciprocal of a very small positive number is going to be a very large positive number. And this describes asymptotic behavior. This means we are approaching a vertical asymptote at x is equal to 0 for the cosecant function. Okay. Now, so anytime that you would have a 0 on an original function, the reciprocal of that function would have to therefore be a vertical asymptote. Notice that's always going to be the case. For any 0 of a given function, there must be a vertical asymptote on the reciprocal function. But we need to know how we are approaching that asymptote from the left and from the right. But we at least know that there has to be a vertical asymptote there. So at every one of the zeros, okay, here we go. All right, this is just going to keep repeating like that, right? Okay, if the sine of x is equal to 0, then the cosecant of x is going to be undefined there, right? So I have vertical asymptote. All right, and it's important to investigate how we are approaching that asymptote. So we said, like, for instance, here, if x is approaching the asymptote from the left, we're going to be going to negative infinity on the cosecant graph. Okay, so we're approaching from the left, then we are going to negative infinity. And if we are approaching from the right, we're approaching x is equal to 0 from the right, then the vertical asymptote, we're approaching that by going up towards positive infinity. And that seems to make sense as well. The y values along this portion of the sine curve, the y values are all positive, and therefore their reciprocals will also be positive. Right? Okay, so the reciprocal of a positive number is positive, and the reciprocal of a negative number, down here, all these y values are negative, and the reciprocal of a negative number is always going to be negative as well. So we're going to have a graph for the cosecant, okay, that remains above the x-axis in this region here, but flips to become below the x-axis, right, for instance, in this region here. And then that pattern is going to continue to repeat, because the sine function, after all, repeats over a period of 2 pi. Okay, so these two graphs are going to intersect with each other at this single point, at the minimum here, and then the cosecant is going to open downwards, and we're going to intersect at the maximum here, and the cosecant is going to open upwards. Okay, and that's just going to continue to repeat. All right, so we can choose what is a typical branch. Okay, one choice that we can make would be to say it's between 0 and 2 pi. Okay, we're going to have to cut out the values in the domain that are restrictions, right, wherever we have a vertical asymptote. Notice that, again, because the period of the sine function was 2 pi, that it must also be that the period of the cosecant is equal to 2 pi as well. Right? So the entire graph of one complete wave of the cosecant function is actually broken into 2 pieces. You need both of these pieces to make up one cycle of the cosecant function. Okay, so this is one complete period right here from 0 to 2 pi, for example. Okay, so we find one complete cycle on the interval of cosecant, that is. Okay, on open from 0, right, from 0 to pi, open at pi, union, open from pi to 2 pi. Okay, 0 to pi, union, pi to 2 pi, for example. Okay, so in red here, okay, I've graphed the cosecant function. Y equals the cosecant of x. We note that it has no max and no min, hence it has no defined amplitude. Okay. All right, we notice that the period is equal to 2 pi. In general, you take 2 pi divided by the magnitude of b if you had a modulation factor of b. Okay. Divide 2 pi by the magnitude of b, you would find the period of the modulated wave. Okay, there's our basic cosecant function graphed as a reciprocal, okay, of the sine function. Okay, and now the graph of y equals the secant of x would be constructed in the same way by taking the reciprocal of the cosine function. So if we started with a rough sketch of the cosine wave, right, which is the same as the sine wave except shifted by pi over 2, right? Then we're going to get the secant function, which is going to look just like the cosecant function, except shifted also by pi over 2. Right? So we would have vertical asymptotes. Anywhere where the cosine is equal to 0, the secant would have to have a vertical asymptote. Okay. So we can start by plotting our vertical asymptotes. All right, and fixed points at every maximum and minimum on the cosine graph. Okay, and then we can graph our little sort of parabolic shaped pieces that we have within each one of these sections. All right, and that's reasonable for a sketch. And then we should label for more accuracy here as well. Okay. So yeah, so the y value here is 1. All right, the y value down here is -1. Right. The vertical asymptote. Let's see. This first vertical asymptote would be at. Let's do this in red. Okay, this would be at x is equal to pi over 2. And then the next one would be at 3 pi over 2. All right. All right, the cosine wave, a standard cosine wave on a principal branch would start at 0 right here, and it would end at 2 pi right here, right? So this is 2 pi. Okay. All right, this is pi right here. Okay. Let's see. This is, of course, 0 right here. All right. Let's see, x equals 5 pi over 2 is a vertical asymptote. X equals negative pi over 2 is a vertical asymptote. X equals negative 3 pi over 2, etc. Okay. Okay, now you can do analysis of the secant function by sketching its graph as well. Okay, one more. That is the cotangent function. We can construct its graph also by doing reciprocal. In this case, the reciprocal of the tangent function. So graph y equals the cotangent of x by noting that the cotangent of x is 1 over the tangent of x, right? The reciprocal of the tangent. So we can start with sketching the tangent. Right, this is, what is this, pi over 2, negative pi over 2 for the vertical asymptotes. Okay, this is, of course, the point 0, 0, right? You get pi over 4, 1, and negative pi over 4, negative 1. Okay, and then that pattern repeats. Okay, x equals what? 3 pi over 2. Okay. Okay, so let's say I go in red. Well, first, okay, so in black we have y equals the tangent of x. Okay, so now in red, Anywhere where there is a zero of the function you're taking the reciprocal of, we are going to get an asymptote, a vertical asymptote for our reciprocal function. So we get a vertical asymptote here, okay, at x equals 0. We're going to get a vertical asymptote here, okay. That would be at x is equal to pi. Okay, we get a vertical asymptote here. That's at x is equal to 2 pi. Okay. We'll get one here. That's at x is equal to negative pi. So vertical asymptotes there. Okay. If the output of the original function is 1, then the output of the reciprocal is also 1, because 1 divided by 1 is 1. All right. Okay, so that's there, that's there, that's there. Okay. And if the output of the original function is negative 1, okay, then the output of the reciprocal function is also negative 1. Right? So, of course, 1 over 1 is 1. 1 over negative 1 is negative 1. Okay? All right. Now, let's take a look between 0 and pi. Right? So the difference between these two asymptotes right here is pi. The period is equal to pi, therefore. Let's take a closer look here. If we were to travel along the tangent curve as we were approaching 0, let's say from above, right? Let's say as x approaches 0 from above, okay, notice that the tangent of x is approaching 0 as well, and that's approaching 0 from above. That is because we're outputting positive y values here. Okay, so as x approaches 0 from above, therefore the cotangent of x would be approaching what? The reciprocal of this would be 1 over a really small number, so it would be approaching positive infinity. Right? So if we take a really small positive number, which is the y value from the tangent curve, the reciprocal of that really small positive number is a really large positive number. So we would be going up towards positive infinity. So that's how we're approaching this vertical asymptote. Now this is going to nice and smoothly and continuously approach this point right here. Now what about the vertical asymptote at x equals pi over 2? If we have that the tangent is undefined, that is getting uncountably large, whether positive or negative, the reciprocal of that would be 0. Right? So we have as x approaches pi over 2, let's say from the left, the tangent of x is approaching positive infinity, as we know from our asymptotic behavior, right? Going to positive infinity. Okay? Then the cotangent of x, being the reciprocal of this, okay, would be approaching 1 over a really large positive number. So this is approaching 0, but remaining positive. As x approaches pi over 2 from above, the tangent of x is approaching negative infinity. Right? We can see from the asymptote here. Okay. Then the reciprocal of a really large negative number, that's the cotangent of x, the reciprocal 1 over a really large negative number would also be a really small but negative number, so approaching 0. So in both cases, the cotangent graph is approaching 0. Okay? The reciprocal of a large positive number is a small positive number, and the reciprocal of a large negative number is a small negative number. So the cotangent graph is going to cross at pi over 2, okay, and then we're going to see that it's going to continue in this direction, right? Again, a really small negative number, the y value from the tangent curve, the reciprocal of that would be a really large negative number, so we expect the graph to continue like this. All right, and that's it, okay? Then that pattern continues, all right? We go through the axis here. There we go. Good. So a 0 of a function is a vertical asymptote on its reciprocal, and vice versa. A vertical asymptote on a function corresponds to a 0 on its reciprocal. Okay, so there's our cotangent. Now, a standard principal branch, the principal branch of the cotangent will be this one from 0 to pi. Okay, so let's make note of that. Principal branch, okay, of the function y equals the cotangent of x would be found on the open interval from 0 to pi. The period is equal to pi. Okay, just like it was for the tangent from which it was derived. So a cleaner sketch of that cotangent graph, right, looks like this. Vertical asymptote at x equals 0, a vertical asymptote at x equals pi. It is a decreasing function from 0 to pi. Okay, it crosses through the x-axis at pi over 2. Okay, important points at pi over 4 and 3 pi over 4, where the output is 1 and -1 respectively. Okay, and then that pattern would repeat. So there would be another vertical asymptote at x equals 2 pi, for instance, and then the pattern repeats again, right, on and on. And the pattern repeats to the left as well, of course. So x equals -pi. All right, there's your cotangent function then. Okay, y equals cotangent of x. And the principal branch is from 0 to pi. Okay. All right, so up here, this was 3 pi over 4 and -1. Okay. All right, so you try out the homework and practice with these other trig graphs, mostly focusing on the tangent graph and some transformations of it, but also a little bit just, knowing the basic, at least the basic reciprocal graphs as well, and maybe some minor transformations of them. Okay, again, the period of the cosecant and the secant is still going to be 2 pi. Right, each of these have a period equal to 2 pi, and the cotangent has a period of pi. It's the same as their reciprocal function as well. And that's all I have for you for this section. So try out the homework and let me know if you have any questions with that. Okay, take care.